In this discussion, we're going to talk about the 5 different types of chemical reactions. We're going to go through each type, what it is, as well as examples and how to tell. So the first type of reaction is a synthesis reaction, also known as a combination reaction. In these reactions, 2 things join to form 1. So 2 join to form 1. Okay. If we notice, we have potassium and we have bromine. We have Br2. In a synthesis reaction, you take one of your metals, so just one metal, one nonmetal, and they join together. The reason that we have KBr is due to the charges. So you always need to look at the charges when you're forming a new compound. So looking at your periodic table, potassium is +1, bromine is -1. Think when we created chemical formulas, your charges have to equal 0. 1 minus 1 is 0. And so we just have KBr. Again, this is an example of a synthesis reaction in which 2 things join together to form 1 thing. As we go through the different types of chemical reactions, as well as predicting products, you guys need to make sure that you know diatomic molecules. And so diatomic molecules, if you look at the meaning, di means 2, atom means just 2 atoms. So whenever any of these elements are alone, they're followed by a 2. And a way to remember this is 7-up. You have hydrogen, nitrogen has the atomic number of 7. It also forms a 7 on the periodic table. These are always diatomic when they're by themselves. So for instance, H2, N2, O2, etc. These are diatomic molecules. You want to make sure you know these. Make sure that you memorize them if you need to. So looking at synthesis reactions, what we're going to be doing is we're going to be predicting products. What that means is we are going to take the reactants, so anything that is on the left-hand side, these are known as the reactants, and we are actually going to determine what our products are. So our products always come to the right of the arrow. And so for synthesis reactions, remember you have 2 things, those join together to form 1. So I have iron and I have oxygen. I'm just going to put 1 of each. So I have FeO. If we look at the second example, we have magnesium, we have nitrogen. Notice that we had O2, now we have N2. Remember, that's because these are diatomic. So I'm going to just write Mg and I'm going to write N for nitrogen. Notice that the 2 is not carried over, right? This 2 isn't carried over to here. And so what we have to do now whenever we form a new compound is we need to look at our charges. So magnesium, if you look at your periodic table, has a charge of +2. It is always +2. Nitrogen has a charge of -3. Well, if you remember the crisscross method that we did, this is +2, this is -3, you crisscross, we end up getting Mg3N2. Now we're going to look at the third example. And so in this third example, we have sodium, we have Cl2. What we're going to do for the synthesis reaction is we're going to combine them together. We have Na, we have Cl. Now we need to look at charges. Sodium is +1, chlorine is -1. If you crisscross, they already equal 0. Now what you can do is you can try and see if you can do those last 2 examples on your own. You can take a look at the discussion that is on your student login, and you'll actually find the answers to those already worked out for you. So the second type of chemical reaction is a decomposition reaction. If we take a look at this word, decomposition, okay, you look right here, decompose. So if you think about what it means to decompose, you have one thing that breaks into two. Okay, so again, you have one thing, it decomposes, breaks down into two different things. So notice here I have KBr. I have potassium and I have bromine. So I know that it breaks down into K, I know that it breaks down into Br. However, whenever you break it down and put elements by themselves, you need to look back and see if either of them are diatomic. So when Br is by itself, you need this small 2, which means it's diatomic. So you end up getting KBr yields Br2 plus K. And it actually doesn't matter if you want to do Br2 plus K or K plus Br. Either way is fine. So what we're going to do now is we're going to look at these decomposition reactions and we're going to predict the products. We're going to figure out what are my products when I start with this initial compound. So if I look at this first example, I have Na2O. So I have Na2O. I need to figure out what are my elements that this breaks down into. I'm just going to write those first. I have Na plus O. Now what you have to do is you have to look back and figure out, are either of these diatomic? Well, if you look at the second slide, you have H and then you have N7. Oxygen falls in there, so oxygen ends up being O2 when it is by itself. So let's take a look at the third one, H2O. If you look, you have H plus O. Well, if you look back, hydrogen is diatomic and oxygen is diatomic. And so what we end up getting is H2 plus O2. And so what you guys can do is you can try and see if you can do number 2 and number 4 on your own. And once you do those, check your answers to the discussion that is posted online. See if your answers are right. Number 4 is actually kind of tricky. So if you don't get that one, that's okay. This is kind of an extension problem for you. The third type of reaction that we have is a combustion reaction. In a combustion reaction, we have a gas being burned. Okay, so a combustion reaction, we're generally burning a gas. Sometimes it could be a liquid, but generally you are burning a gas. In order for a combustion reaction to work, if we look at this first example, we're going to go through this just to explain combustion reactions. In order for it to work, you have to add oxygen. Remember, oxygen is O2. So you're going to add oxygen in order for this to work. For every combustion reaction, you always produce CO2 and H2O. Okay, those are always your products. This example, this is always how combustion reactions are going to look. You're always going to need O2, you always form CO2 and H2O. So if we take a look at the second example, we have C6H12O6. Okay, so remember, these numbers should be small. It's just formatting. So we have C6H12O6. You always have to add oxygen. Even if there's an oxygen already in here, you still need to add O2. So we have our hydrocarbon plus oxygen. We always form CO2 plus H2O. And so using what we did in those first two examples, see if you can do the third and fourth example. Again, look back to the discussion and check your answers. So the next type of reaction that we have is a single replacement reaction. And in a single replacement reaction, what happens is our metals switch places. So we have metals switch. And Notice in a single replacement reaction, we're going to treat this almost as if we have couples. So let's say that this person with the blue head is the girl. So here's our girl. We have a boy and a boy. Same thing on this side. Okay, our boys are going to act as our metals. So I have a boy here. Okay, here's boy 1, here's boy 2. Notice what happens. They switch. So I have a single boy, I have a boy in a couple. Over here, notice I have a different single boy, and my original single boy is now in a couple. So think about this in terms of relationships. Our metals, or our boys, simply switch places. Notice that our metals, our boys, do not join together. The metals simply switch places. So what we're going to look at now is we're going to look at some single replacement reactions. First thing we're actually going to do is we are going to identify our metals. So in this first example, we have magnesium plus copper sulfate. So what I would recommend doing is underline your metals. Okay, I have a metal by itself, which is magnesium. I have a metal in a compound, which is copper. These are my metals. They simply switch places. So magnesium, I'll write it over here, magnesium now joins with sulfate, which is SO4, and copper is now by itself. Now remember, whenever we form a new compound, we need to look at our charges. So magnesium has a charge of +2. If you look on the back of your periodic table, or if you look at the reference sheet that is posted on your student login, you'll find that sulfate is -2. Well, +2 minus 2 is 0, and so these are my two products. So now let's take a look at the second example. Again, I'm first going to underline my metals. I have zinc, and in HCl, hydrogen actually acts as a metal. So in single replacement reactions, hydrogen acts as a metal. So what happens in single replacement? You switch your single with the one that's in a couple. So we have zinc combining with chlorine, and we have hydrogen by itself. Now if we take a look at diatomic molecules, hydrogen is diatomic. If we look at our charges on our Zn and Cl, zinc always has a charge of +2, chlorine is -1, so if you crisscross, you get ZnCl2. And predicting products takes a lot of practice. Okay, so it's not unusual if it takes you a few times to get these products. So please don't get discouraged, just keep trying. Okay, keep remembering, metals switch places, you have to use charges to figure out the chemical formula. And so what you can actually do is you can try numbers 3, 4, and 5. See if you can get those. Check your student login, that discussion, the notes, or the teacher version. Check for the answers on there. Also with single replacement reactions, we want to look at if these reactions always occur. So again, if we look at this, we have magnesium, we have zinc. Those are my metals. If this is single replacement, think about what that means. Okay, your metals are going to switch places. Now, in order for our metals to switch places, we have to use what is called the activity series. And if you look on the back of your green periodic table, or if you have the reference sheet pulled up on your computer, the activity series is an arrow, I believe on the left side of the reference sheet, but it's an arrow that has a lot of elements listed. What this shows is this shows how active your elements are. The ones that are at the top are more active. Ones at the bottom are less active. Now, in order for a single replacement reaction to occur, Metals have to be more active to switch. Okay, the metals must be active. Okay, and that's your single. Your single element must be more active in order to switch. Now, you guys are probably going to think this is funny, but think about the couples analogy that we used. Okay, so we had, know that you love my stick figures. We had two boys, and then we had, one of the boys had a girl, and then we had a boy and the other one with the girl. Okay, now let's say that we have, this is, we'll say spiky hair is boy 1, bald one is boy 2. Now, in order for this reaction to occur, in order for this boy to switch places and to kick him out, this single boy has to be more active. So think about, this boy needs to really want to be in that relationship to kick this one out. That's exactly what the activity series means. You might hear some teachers say the arrow of sexiness. So in order for Mr. Firehead here to get the girl, he needs to be sexier. So if he is sexier, if he's higher up on this arrow of sexiness, he's going to kick this other guy out and he's going to get the girl. So in this reaction, notice that redhead kicks the other boy out. So boy 1 is sexier, he kicks this other boy out, and he gets the girl. That is the exact same for metals. So if you look on your reference sheet, magnesium is higher than zinc, which means these switch places. So zinc ends up by itself, then we have Mg, and we have NO3. Now remember, whenever we form something new, we need to look at charges. So we have +2, we have -1. So we end up with MgNO3 in parentheses with a 2 on the outside. So if we look at the second example, we have magnesium, we have lithium. If you look at your arrow of sexiness, okay, lithium is higher up. Lithium is sexier. So this will not occur. Okay, lithium is sexier. That means it stays in the relationship. Okay, it's more likely to be in a relationship than magnesium. The last type of reaction that we're going to talk about are double replacement reactions. These are very similar to single replacement, except now we simply have two metals that are both in compounds. So if you think about the analogy that we've been using, we have two guys, but now they're both in relationships. So now what's going to happen is our metals are still going to just switch places. So again, in double replacement, our metals or our positive ions switch places. So finally, we have some examples of predicting products for double replacement reactions. Just like we did with single replacement, I would recommend underlining your metals. That way when we switch them, it'll be a little bit easier. So we have BaCl2 plus K2SO4. Remember that these numbers, the 2, this 2, and this 4, they should be subscripts. Just the formatting caused them to be uppercase. So what we're going to do is we're going to write our metals. Okay, so barium is now going to join with sulfate. So Ba is now going to join with SO4. And potassium, K, is now going to join with CO. Remember that your subscripts on the reactant side don't transfer to the product side. What we have to do is we have to look at charges. So if we look, barium is +2, sulfate is -2, so that's okay. Notice that I have SO4 all as one thing. Potassium is +1, chlorine is -1, so those are fine. So right there, those are my products, BaSO4 plus KCl. What I want to look at now is I want to look at number 2. We have CONO32 plus NH42CO3. So I'm going to go ahead and I'm going to underline cobalt. Okay, your metal always comes first, or your positive ion always comes first. So we have cobalt and we have NH4. That's ammonium. What we're going to do, our metals are going to switch places. So cobalt, CO, is now going to join with CO3, and NH4 is now going to join with NO3. Notice this is CO3, that 3 stays with carbonate, just like the 3 stays with NO3. So if we look at charges, cobalt is +2, carbonate is -2, those are fine. NH4 is +1, that's on the back of your periodic table or on your reference sheet. Nitrate is -1, we don't need subscripts there. So far, we've already predicted products of 2 double replacement reactions. And so what I want you guys to do is I want you to try these last 4. See if you can predict these products, and then check your answers on the PowerPoint on your student login. The last thing to look at with double replacement reactions is we want to talk about why these sometimes make a precipitate. What that means is we sometimes form a solid. So precipitate means a solid. The reason that this occurs is because of our solubility rules. This is where that reference sheet, or if you have your periodic table, is really going to come in handy. Your solubility rules are on the back. When you look at your solubility rules, if it has an S, if it has a Q, that means it is soluble. Okay, soluble is AQ. That means it dissolves in water. Then we can also have not soluble. Not soluble means it's a solid, which means it forms a solid. Okay, that is your precipitate. And so what you do is you just look at the products that you've predicted. So when you look at the products that you predicted, you look at your solubility rules to figure out, does it form a solid? Is it not soluble? If you form a solid, or if you form a precipitate in that reaction, your reaction will occur. So you just want to practice using your solubility rules, and if you look on the teacher notes of the discussion, it actually shows you an example of soluble versus not soluble. Also, now that we've looked at the 5 types of reactions on your student login, you'll also find a video that shows demonstrations of each of the 5 types of reactions. So you now can see demonstrations. You have this video, you can go back and watch certain parts. You have the teacher notes on your student login to help you fill out your handout. And then you're going to be working on the worksheet. The answer key to that worksheet will get posted on Wednesday. That way, you'll have some time to work on it before you check your answers. If you have any questions, please feel free to send me an email, and I will try to answer your questions the best that I can.